Good evening, everyone. I welcome you all for the week 9 live session. Uh, Today, we are going to discuss numerical problems and some theory about micro heat exchangers. Before we go to solving the heat exchanger portion, let us define how microchannels are defined. As you see on screen, there are some demarcation geometries which define uh, channels based on hydraulic diameter. But however, in different textbooks or in different problems, there are different considerations for choosing mini channel or micro channel. This is the most widely used definition of mini channel and micro channel. However, there are some other definitions also which are widely accepted based on few dimensionless numbers such as Boiling number, etc. So the definition of conventional channel is something like this: if the hydraulic diameter of the channel is more than 3 mm, then we call that geometry to be a conventional channel or a conventional tube. For mini channels, if the hydraulic diameter ranges from 3 mm to 200 micron, such a type of geometry we are going to consider as a mini channel. And for micro channel, the hydraulic diameter is of the range of 200 microns to 10 microns. Uh, Transition channels are also defined where the hydraulic diameter ranges from zero point 0.1 micron to 10 micron, and in transitional microchannels we have one more demarcation line. If the hydraulic diameter is between zero point 0.1 micron and 1 micron, we call it as transitional nanochannels. And uh, for molecular nanochannels, the hydraulic diameter is considered to be less than zero point 0.1 micron. So there are some unique features of using micro heat exchangers. They obviously handle very small flow rates of fluid, generally of the order of milligrams per second. They are microchannel passages. We have defined what a microchannel is. Also, for making these kind of heat exchangers, micro manufacturing techniques are most generally used, which include micro milling, stereolithography, etc. And generally in macro heat exchangers or conventional heat exchangers, the uh, preferred or most commonly used hydraulic cross sectional area is circular. But in case of micro heat exchangers, we are not going to use a conventional circular cross sectional area. It is mostly non-circular cross sectional area. Coming to the heat transfer and pressure drop perspective, uh, we cannot directly apply Navier-Stokes equation when we have a channel, we have a micro channel flow. Also, there are two more important boundary conditions, that is no slip boundary condition, which is true for conventional flow. That means the velocity of the fluid next to the wall is equal to the velocity of the wall, meaning that uh, in case I have a wall and a fluid passes over this wall, the no slip boundary condition says that the relative velocity between this fluid and this wall is zero. However, we are not sure about no slip boundary condition in the case of micro heat exchangers. That means there is a slip condition based upon the geometry and the flow characteristics. I will show you under what conditions these are not applicable, or under what conditions we should be more aware. Also, the temperature of the fluid, that is called the jump boundary condition, which says that the temperature of the fluid right next to the wall should be equal to the temperature of the wall. However, even this boundary condition, that is jump boundary condition, need not be true in the case of micro heat exchangers. That means there could exist a certain temperature difference between the fluid and the wall. I mean fluid next to the wall and the wall itself. So there are some different kind of flow regimes based upon a special number called the Knudsen number. So Knudsen number is defined as the ratio of mean free path to the length of to the characteristic length. So if Knudsen number is less than 10 power minus 3, then the regime is in continuum regime, and we are free to apply our conventional Navier-Stokes equation, which we are well conversant with. Also, the energy equations can also be applied for this kind of flow with no slip boundary conditions and no jump boundary conditions. So this we have been discussing about this regime in most of our classes, but in the case of micro heat exchangers, we are not sure about the regime a priori. So in the case of slip flow, which says that which occurs when the Knudsen number is in between zero point 0.1 and 10 power minus 3, we can still apply Navier-Stokes equation and energy equation with considering slip and boundary conditions and jump boundary conditions. In the case of flow regime where the Knudsen number is ranging from zero point 0.1 to 10, we are no longer free to apply the Navier-Stokes equation and energy equation directly. There are certain other equations called the Boltzmann equations, which we need to apply for transition and free molecular flow also. So free molecular flow occurs when the Knudsen number is more than 10. Also, under these conditions, if the flow is compressible, that means if the Mach number is more than zero point 0.3, Mach number is also a dimensionless number, which is the velocity of flow to the sonic velocity. If that is more than zero point 0.3, then the effects of compressibility have also needs to be taken in our Navier-Stokes equation and other governing equations. So Mach number greater than zero point 0.3 means that the change in density is more than 5%. So in such cases, we consider that in engineering problems, if the density is more than 5%, we say that the fluid flow is compressible, and we need to change our governing equations which accommodate for the compressibility. I have spoken about the velocity slip. That is, we are no longer free to apply no slip boundary condition when we are in transition flow or free molecular flow. So this case occurs when the characteristic length becomes of the channel becomes comparable to the mean free path of the fluid. In such cases, velocity slip is likely to happen, or I can say it will happen. The interaction between the wall and fluid molecules become more prominent than the intermolecular collisions. So as a result, we get velocity slip. So this is the formula for velocity slip, which is given as us is equal to 2 minus fm, that is tangential momentum accommodation coefficient, by fm times lambda into dou u by dou y at the wall. So this is the characteristic equation, or this is the formula by which we are going to uh, quantify the velocity slip. Also, we are going to quantify the jump that happens in this kind of flows. that is there is a temperature difference between the fluid at the wall or next to the wall and the wall itself. So the difference is given by C jump, which is actually dependent upon a thermal accommodation coefficient, that is Ft, times dou T by dou Y at the wall. So the thermal coefficient, accommodation coefficient, is given as Q incident minus Q reflected by energy incident by energy of the wall. So from this definition, we are going to find out uh, the thermal accommodation coefficient, and from the thermal accommodation coefficient we are going to find out the jump. There is one more important uh, dimensionless number which we need to consider before we uh, go further to find out the heat transfer coefficients in the heat exchanger in micro heat exchangers. We are well conversant that for conventional channels, Nusselt number is a function of Prandtl number and Reynolds number. We generally write Nusselt number as some coefficient A times Reynolds number to the power B and Prandtl number to the power C, where A, B, C are some coefficients, real coefficients. However, when we are in micro heat exchanger, when we are discussing about micro heat exchangers, we this is not directly true. We also have to consider one more number called the Brinkman number, which is important for microchannels that have high surface area to volume ratio. So it is defined something like this: dynamic viscosity into um square by thermal conductivity into delta T. So Brinkman number is basically a ratio of the viscous heat that is generated due to shear to the heat transfer in the fluid. This is basically we do not give such treatment for conventional channels because most of the heat transfer takes place in the fluid compared to the viscous heat that is generated inside the fluid. However, when the regime is free molecular regime, the fluid molecules interaction with each other becomes comparable with the interaction of the fluid with the wall. So as a result, we need to consider those interactions also while considering the heat transfer coefficient, that is the ability of the fluid to give away heat quickly or accept heat energy quickly. So I'll give you a numerical problem. I'll suggest you all to read and work it out. I'll give you a few minutes. Air flows at a mean temperature of 40 degrees Celsius through a heated micropipe with a diameter of 0.24 mm. The Knudsen number and Brinkman numbers are 0.04 and 0.01. The Reynolds number is calculated to be 600. At 40 degrees Celsius, the thermal conductivity is 0.067 watt per meter Kelvin and the dynamic viscosity is 1.91 into 10 power minus 5 and the Prandtl number is equal to 0.719. So based upon the data given, we are required to find out the heat transfer coefficient of air for constant wall temperature conditions in fully developed regime. So when we are in a case where there is constant wall temperature condition, we are going to look at this side of the table. So we need to know uh, so we are looking for that Nusselt number where the Knudsen number is 0.04 and the Brinkmann number is 0.01 for a constant wall temperature condition. So Knudsen number being 0.04 and the Brinkmann number being 0.01. So our Nusselt number is 6.03. So after getting the Nusselt number, we are now in a position to find out the heat transfer coefficient. So Nusselt number can be written as Hd by K, where the hydraulic diameter is also given, that is 0.24 mm. We have plugged that value in the numerator, and the thermal conductivity of the fluid is also given as 0.067 in SI units. So from that we find out that the heat transfer coefficient is 1683 watt per meter square Kelvin. Okay. For the same problem, instead of having a constant wall temperature, if there is a constant heat flux boundary condition, we are required to find out the heat transfer coefficient. Okay. When we have a constant heat flux boundary condition, again we are going to find out the Nusselt number from the other side of the table. When we have a Knudsen number of 0.04 and Brinkmann number as 0.01, so that comes out to be 3.7398. So this is our Nusselt number. So once we find out the Nusselt number as 3.7398 and the hydraulic diameter being 0.24 mm, and the thermal conductivity of the fluid is also known. So once we plug in the values, we get the heat transfer coefficient as 1044 watt per meter square Kelvin, which is lesser than the heat transfer coefficient that we got uh, when we had a constant wall temperature boundary condition. Okay. Let's take up one more numerical. We have helium gas that is flowing through a channel of 100 microns with a velocity of 40 meters per second. The mean free path of helium gas at these conditions being 0.194 microns. We are required to find out the temperature of the gas given density, dynamic viscosity, and adiabatic index of helium. So to find out the temperature of the gas given mean free path, we have this formula of mean free path given as dynamic viscosity into root pi divided by rho times root 2 RT. So the mean free path of any gas is given as defined as lambda equals mu times root pi divided by rho into root 2 RT, where R is the characteristic gas constant, which is got from dividing the universal gas constant with the atomic weight of that gas. For helium, the atomic weight is 4, so we are dividing the universal gas constant with 4 and getting the characteristic gas constant as 2.07 kilojoule per kg Kelvin. So once we plug these values in this formula, uh, we have the dynamic viscosity given, uh, and rho of uh, helium at this temperature is also known. The characteristic gas constant is found out, and this is for the dimensional uh, homogeneity, and this is the temperature that we are looking for. So once you plug these values, we get a temperature of 300. Okay. Uh, so next question is to determine the Mach number of the flow. This is a fairly easy problem. The Mach number is directly the ratio of uh, flow velocity to the sonic velocity. So we are required to find out the sonic velocity in helium. So the Mach number of flow is defined as the actual velocity to the sonic velocity. So the sonic velocity is got by root gamma RT. So once you plug in the values of gamma, R and T, we'll get that to be 934.32 meters per second. Oh, this should have been not 1.4, this is 1.67. So kindly make a correction there. It is a monoatomic gas. It is the gamma is not 1.4, it is 1.67. So you can correct the sonic velocity accordingly. So the Mach number comes out as actual velocity, which is already given to us, to the sonic velocity, which we found out from this. So next up, we are required to find out the Knudsen number of flow. So Knudsen number is defined as lambda by characteristic length. That is, lambda is mean free path, which we already found out to the characteristic length. Or you can write Knudsen number as Mach number by Reynolds number into root pi gamma by 2. So the Knudsen number is given by this formula, Mach number by Reynolds number into root pi gamma by 2. So we know the Reynolds number formula, rho into U infinity in times hydraulic diameter by dynamic viscosity. So we plug in the values of rho, mu infinity, U infinity, and the hydraulic diameter and the dynamic viscosity that are given. So we get a Reynolds number of 32.66. Once we plug this value in this formula, where the Knudsen number is given as Mach number by Reynolds number into root pi gamma by 2. The Mach number is already known from this equation. We have already got the Mach number as 0.042. So the Knudsen number is finally 0.00208. So I would also like to draw your attention that we are in this region where the Knudsen number is greater than 10 power minus 3 and less than zero point 0.1. So we are in that regime where we are Knudsen number is about 2 into 10 power minus 3. So we are in slip flow condition. So initially the temperature of the helium gas was at 300 degrees 300 Kelvin, that we came to know from this numerical. So if the temperature of helium gas is raised to 600, what will be its mean free path? So we know the formula for mean free path, lambda equals mu times root pi by rho into root 2 RT. So the characteristic gas constant of helium also is known. It is 2.07 kilojoule per kg Kelvin, that we have already found. So for a temperature of 600 uh, Kelvin, once you plug the value of 600 in this formula, we get that the mean free path of helium is about 0.137 microns. So when the temperature is increased, we come to a conclusion that it was initially 0.194 at 300 Kelvin, and now it is 0.13 micron, because of at elevated temperatures the gas molecules have higher kinetic energy, and the frequency of collisions become more. So as a result, we can expect this solution that the mean free path will be lesser than what it initially was. So these are the books and references which we can follow. Thank you.